Section 3.4. In this chapter, we've limited our focus to second order ODEs. Actually, much more specific than that. Second order LHCC ODEs. Given this type of focus, we know that the characteristic polynomial of any ODE of this type will be a quadratic, something like a r squared plus br plus c. As we've pointed out a few times, there are three distinct cases when it comes to the types of solutions a quadratic equation can have. Listed here, we could have two real distinct roots. We could have a pair of complex conjugate roots or one real repeated root. So far in this chapter, we've discussed how to deal with the first two cases. Watch. EG1, for example 1, is a characteristic polynomial that has two real distinct roots. R equals plus square root of 6, R equals minus square root of 6. Its general solution is simply a linear combination of exponentials with those roots up in the exponents. For example 2, EG2, we have a characteristic polynomial that has complex roots. Remember that we know such roots will always occur in this form. Some real number plus or minus some real number times I. That's called a complex conjugate pair. So you'll hear me use that term sometimes. The general solution here is a little bit more complicated. We identify the real part of our roots. We called that lambda in the last lecture. That is the number up here in this exponential. Then the imaginary part, we called that mu, is in the argument or in the angle of these two trig functions, cosine and sine. That leaves the third case, a real repeated root. So how does such a root happen? Our characteristic polynomial must eventually have the form r minus k squared equals 0. I say eventually, maybe it doesn't initially look like this, but after some algebraic manipulation, my characteristic polynomial, my characteristic equation must be able to be put into this form. If I kind of reverse the process a little bit, I can actually retrieve the original differential equation, and so it'll have a form like y double prime minus 2k y prime plus k squared y. So solving this characteristic equation gives me the value of r equals k, and that's it. There's only one root, just the value r equals k. As I indicate in this paragraph here, you might be tempted to simply say this type of quadratic does have two roots, k and k again. So we can simply construct our general solution in the customary way, build exponentials with k in the exponent. This is not feasible. You'll actually take a closer look at this in an upcoming written homework problem. The reason being that these two building block functions in my solution are not actually two distinct functions. As I've noted here, we could merge those together and end up with a single building block function. If I write my solution in this way, on the surface it looks like I've got two separate components, but really I've just got a constant times e to the kt. So I only have a single building block function. This notion of fundamental building blocks that we use to construct our general solution is the main idea in the next section. For now, trust me that for a second order LHCC ODE, we need two distinct building blocks to construct our general solution out of. We've got one of our building blocks. Here I've labeled it y sub 1. E to the kt will work as one of the building blocks for our general solution. How about a second building block? Multiplying by a constant won't work, even though that would give me another guaranteed solution. What if we multiplied by a function? Well, if we're taking that route, I suggest we select the simplest function possible. I vote for just t, just the function t. So let's try it. Let's define y sub 2 to be t e to the kt, as I've written here. And let's see if this is a solution to our differential equation. Recall from a few steps back that my LHCC ODE will have this form here. And then I want to see if this is a solution. I'll just use the usual process where we find the necessary derivatives, plug them in, and see if the differential equation ends up being true. Here I've done all of that work. I found what y sub 2 prime would be, just applying the product rule. I found what y sub 2 double prime would be. In y sub 2 double prime, I actually have like terms here, so I can add those together. And then I plug those into the left-hand side of my ODE. That yields this big expression here. And then if I've done everything correctly, when I distribute and then collect like terms, sure enough, the left-hand side all cancels out. And so it equals 0. So my differential equation is satisfied, and so this y sub 2 is a solution to my differential equation. Cool, so we have a second solution that we can use as a building block for constructing our general solution. As I've indicated here, we'll have to wait until the next section to verify that these two solutions are, quote, nice enough, that's our author's term, to serve as a fundamental set of building blocks for our general solution. So for now, you'll just have to trust me. Theorem 1 summarizes this conclusion. It says if the characteristic polynomial of the LHCC ordinary differential equation has a single repeated root, here I've named it k, then the general solution of the differential equation is e to the kt as we would expect. And then in my second term here, I'll also have an e to the kt, but I've introduced a t as a sort of a coefficient. I've multiplied by this t. Let's try this out with an example. Here we're given an LHCC ODE with initial conditions, but notice that the actual values of the initial conditions are not stated. Instead, we're asked to describe possible shapes for solutions in terms of these initial condition values. Basically, we want to give a qualitative description of the different types of solutions we could get for this ODE. As usual, we start with our characteristic polynomial. We factor and solve that. And sure enough, we have one real repeated root, r equals -6. From Theorem 1 above, we know the general solution will be this here. We've got c sub 1 e to the -6t plus c sub 2 t e to the -6t. Let's go ahead and incorporate these initial conditions. First, I can identify from y of 0 that c sub 1 will have to be alpha. To incorporate the second initial condition, I'll need to find the derivative of my general solution. Here, I've already plugged in that c sub 1 equals alpha, and then I've taken the derivative of my general solution. Here in the parentheses, I'm applying the product rule. Now let's plug t equals 0 into this and set this equal to beta. Here I went ahead and simplified some of these terms. When t equals 0, this exponential will just be 1. When t equals 0, this whole term goes to 0. This will go to 1. So this whole second term will just be c2 times 1. So I have a c2 value of 6 alpha plus beta. Let me go ahead and write my actual solution. Here is my final actual solution with those initial conditions incorporated into my general solution. And now for the last part of this problem, we're asked to describe possible shapes of these solutions. We just want to give a qualitative description of the different types of functions we could get from these solutions. First, note that for all values of alpha and beta, these solutions will tend to 0. As t grows without bound. We have two exponentials that have negative exponents in a sense. They have negative coefficients on t in the exponent. So they'll both vanish as t goes to infinity. And actually, this first term is pretty boring, plain old vanishing exponential. Note that this will be the entire solution if this second coefficient equals 0. So that's one possible shape. So if 6 alpha plus beta equals 0, this second term of the solution is eliminated. So we simply have alpha e to the -6t. That yields two different types of solutions, one where my alphas are positive and the other where my alphas are negative. If this coefficient 6 alpha plus beta is not 0, then my functions are a little bit more interesting. This second function here will vanish as t grows without bound. That is, for large t values, this exponential will dominate and it'll push the solutions to approach 0. But for small t values, this linear function dominates. So the function will actually grow positively or negatively based on this coefficient. So it'll grow for small t values, then turn around and approach 0. Here, let me draw what I mean. Here I've drawn a couple possible solutions where for small t values, the functions are growing. In this case, they're growing positively. And then there is a critical point. There is a maximum at which the function turns around and then starts to approach 0. If it happens that the coefficient is negative, then the functions will grow negatively. But once again, there is a critical point in the solution before the function turns around and approaches 0. That's in contrast to these solutions over here, which do not have critical points. These solutions are always decreasing or always increasing. And then which of these two types of behaviors I actually see is just contingent on the sign of this coefficient, whether it's positive or negative. So those are all of the qualitatively different possibilities for solutions of this differential equation. So this section demonstrated how to handle the third type of roots we can get from a quadratic characteristic equation, a single, real, repeated root. In the next two sections, we'll discuss theoretical reasons why two building block functions are necessary for our general solution. We'll also introduce a tool that tests whether two candidate solutions can serve as such building block functions.